I'm happy to see so many faces here. My name is Jakub Klemsa, and I did this research when I was at Euracom as a postdoc together with Melek Önen, who's also present here today. So hello to Melek. And currently I'm unemployed, but starting from Monday I will be joining Zama. So that's some additional information about me. Let's start with the talk. The topic of the talk is PARMESAN. That's a library which implements some parallel arithmetic operations over encrypted data. For this, we'll need two fundamental ingredients. One of the ingredients is homomorphic encryption. We have chosen to use the TFHE scheme. And then the second ingredient is the parallel addition algorithm. Actually, there is a family of algorithms. We choose one. For TFHE scheme, I give a very brief overview. All right, so TFHE operations. TFHE supports two operations over encrypted data, over ciphertext. One of them is addition, and the other is lookup table evaluation. And so it's relatively cheap, but there is a noise that grows. Yeah, the other is lookup table evaluation, which on the one hand, it refreshes the noise to a certain fixed level, so it doesn't destroy the message. We can keep on doing the additions, and it's also known as bootstrapping, this procedure to refresh the noise. But it's a bit more expensive. It might take tens of milliseconds on ordinary CPU. And there's another limit. To achieve practical TFHE parameters, the lookup table size is limited to maximum 8 bits, usually even a bit less. And the problem is that the complexity of bootstrapping grows exponentially. So given a function f to evaluate this over encrypted data, we need to decompose this function into additions and lookup table evaluations to use this with TFHE. The other ingredient is parallel addition, and which is the basic ingredient of arithmetics. So that's why we focus on this in the first point. Due to the limited lookup table size, which is also the message space size of TFHE, we would need to resort to digit-based arithmetics. Otherwise, we would only have 8 bits of precision. So for higher precision, we need a digit-based mix. With a standard multi-digit addition, there is the problem. There is a carry. To evaluate the carry, we illustrate this here on the right side. So if you add 1 plus 1 in binary, you have 2, which is 1, 0. So you write 0 and you propagate the carry all the way to the left. So to evaluate the carry, there's a problem that it's nonlinear. So for this purpose, we need to evaluate the lookup table, which we know is costly. And even bigger problem is that it's inherently sequential. So the operation need to wait for each other to evaluate. And the question is, what can we do better if we have enough sufficient parallel resources? How can we use them efficiently? And the answer to this question is we may use parallel addition that was introduced back in 1961. And since then it was a bit extended, generalized, and improved. Okay, let's go a bit deeper. Parallel addition is not a single algorithm. As I said, it's a family of algorithms defined by an integer-based beta and a finite set of digits, also known as alphabet. There's a special thing about these alphabets. This alphabet compared to the standard alphabet is a bit extended. There are more digits than needed for representation of an integer. And there are also negative digits. These digits are denoted with a bar, and now I show an example. So, for example, for beta equals 2, with the alphabet containing -1, here's the small bar. This means -1, 0, and 1. This is also known as signed binary, which will appear later as well. We may write 1, -1, 0 in binary, which would evaluate as 1 times 2 to the 2, plus -1 here times 2 to the 1 plus 0 times 2 to the 0, which evaluates to 2. But we may also write 2 in binary or signed binary as 1, 0. And that's important property of these representations, which is redundancy. Actually, it was shown that the redundancy of the representation is a necessary condition for a parallel addition algorithm to exist. So it means, in turn, that in the standard base beta representation with the standard alphabet from 0 to beta (-1), so for example, base 10, we would have 0, 1, up to 9 digits. No parallel addition algorithm may exist. All right, what's the magic behind parallel addition, or what's the property that allows parallelization is the locality of the algorithm. We can think of this as there exists an integer p, so that only p consecutive digits of the input are sufficient to evaluate one digit of the output. It's depicted here. Here we have 3 digits of the input, which are sufficient to evaluate one digit of the output. This means that with this property, we may evaluate each digit of the result in parallel, compared to standard sequential, where we need all the way down to the right of the input numbers to evaluate the result at certain position. So this is not parallelizable. Okay, now as we have the basic ingredients, let's move on to the operations, how this will be evaluated over TFHE encrypted data. First, we start with the fundamental operation, which is addition, which we already introduced, and now we look how this can be turned into the encrypted domain. As input, we have x and y in signed binary, and we want to calculate z as x plus y. And again, the result is also in the signed binary. What we need to implement over encrypted data is for each digit, we need to evaluate this intermediate sum, denoted wi, then the value of qi, which is some super complicated formula, which inputs wi, which is here, and wi minus 1. And all of this is combined into the result. This is one digit of the result z, and this is calculated as the intermediate sum, and these local carries. You may wonder why this is parallelizable, why this is local, because in standard addition there's also carry that propagates from the right to the left. This is the same here, but with the difference that the carry does not depend on the previous carry, it only depends on the input. So we may see that to evaluate zi, we need the values at the index I for this value, at the index I and I minus 1 for qi, and at the index I minus 1 and I minus 2 for qi minus 1. So altogether, we need 3 positions to evaluate one digit of the output, which is the locality property that we need for parallelization. So this is over plain data, and then we need to turn this over encrypted data. So we need to decompose these operations into what's supported by TFHE. So basically addition and lookup table evaluation. Wi and zi is pretty simple. That's linear. For this we can use addition. Only for qi, that's tricky. We need to combine lookup tables and additions, because the problem is that the lookup table is in TFHE is one-dimensional, whereas here we have 2 inputs, so that would be 2-dimensional, and that's why this makes it a bit tricky. And to choose a proper method, we have a separate paper on this topic where we identify the fastest approach among 2 parallel addition algorithms, one with base 2, one with base 4. And for each of these algorithms, we consider 3 strategies how this can be combined with the lookup tables and additions. In the end, what we chose is the strategies that uses the signed binary representation and one bootstrap to evaluate the value of qi. Here, the value of qi is depicted in the 2-dimensional table, and what we need to do is to sort of linearize this into one-dimensional lookup table. And this gives the magic formula that tells us what we evaluate to achieve the result in single bootstrap. Basically, we evaluate this linear combination with addition, and then we put this as an input to a lookup table. We just compare this whether it's lower than -4 or greater than +4 or somewhere in between. Then the result would be -1, which is the region here, or 0, which is the region here, or 1, which is the region here. And interestingly, there's one property of lookup table evaluation in TFHE I didn't notice yet, and that's the lookup table needs to be negacyclic, meaning that the first half, only one half of the lookup table can be given. The other half of the lookup table is given inherently by its negative image, so it's basically anti-periodic. And here in this case, we can see that there is +1 on one side and -1 on the other side. So there might be the negacyclic overlap. So we might use a shorter lookup table than needed in case we didn't make use of the negacyclic overlap. This gives us shorter plaintext clear text space as opposed to the naive approach. So we might use only 5-bit clear text space, which gives in turn better parameters and better performance. Now let's move on to more advanced operation, which is scalar multiplication. This is the most interesting operation, and also the research was most exciting. By definition, scalar multiplication is a multiplication of a plain integer k and encrypted number represented as a sequence of n TFHE ciphertexts. And the definition is that we take the operation of addition and we take k encrypted values c and we just add them together. Following this definition, the implementation would take k-1 additions. That would be extremely naive. So what can we do better? First, we might reuse some intermediate results, as we can see here. This is the naive approach, that we first add these values, then we add the other value, and then we add the last value, for which we need 3 additions. Or we might reuse some intermediate result. Here we calculate c plus c, and we reuse it here. So we basically only evaluate this addition and this addition. This we copy-paste. So this is the first improvement. Actually, similar problematics is studied in elliptic curve cryptography, and this is known as addition chains. And the goal is to optimize the number of addition operations. There is a related problem that is NP complete. So finding the optimal addition chain is assumed to be a hard task. What we can do next is subtraction, because in certain ECC representations, there's only addition, or there's addition of the points on the curve. In some of them, subtraction might be difficult. So in the basic representation, there's only addition chains. But in our representation, in our arithmetic, we might use subtraction as well, which gives addition-subtraction chains. In some cases, it might lead to shorter evaluation. So for example, for 31 times c, we evaluate 32 times c, which we can do some simple way, and then we just subtract 1c. And the last, actually, for some ECC representation, subtraction is also efficient. So until here, there is nothing new. And the new thing we have is that in the radix-based representation, we have another feature on top, which is free doubling. Basically, if we want to take a double of some encrypted value c, we might just shift this to the left, adding a trivial LV sample of 0, trivial unencrypted 0 on the right. So that's why it's not completely free. But it's almost free compared to some other like locations. So what we define is a free doubling addition-subtraction chain. We denote this ASC star. Now we have a look a bit more formal definition, we just skim through this because it might be too technical. So for addition-subtraction chain, which we might know from ECC, there is a length L and integer k for which it's defined. And it's basically a sequence of numbers starting from 1, which is k0, and then those L numbers, k1 up to kl, where the last number is the desired integer k. What it needs to satisfy is that for each index, the value of ki needs to be, there need to exist 2 previous indices, such that the value ki can be achieved by addition or subtraction from these 2 previous values. It would be better to see an example. So for the number k equals 7, we have this addition-subtraction chain of length 1, 2, 3, 4. And we might notice that each of these values can be reached as addition here or subtraction here of some of the previous values. So this gives us a recipe how to evaluate number 7 starting from 1. The additional feature of our chains is free doubling, which means that together with 1 in the beginning, which is a trivial chain, we also have 2, 4, 8, and any power of 2 basically for free. So what we define is an equivalence class for a not integer, which contains the odd integer k in the beginning, and then 2k, 4k, 8k, and so on. Any multiple of k by power of 2 is present in this equivalence class, which we obtain almost for free. So we define this ASC star as a sequence of these equivalence classes, where the properties are very similar, except for this addition. There's not only we can add any previous values, we might also take any power of 2 multiplying one of the previous values. And in the end, we do not need since all these representants are odd numbers, then the final value might be achieved as a power of 2 times the final integer kl. So since this k might not be odd, so it just needs to be element of the equivalence class. Again, it would be better to see an example. So again, for the number 7, we have pretty short addition-subtraction chain with free doubling, because 7 can be written as -1 plus 1 times 2 to the 3. Again, this -1 is this one, and this is taken from this equivalence class. So together with 7, there's also 14, 28, and any power of 2 multiplied by 7. Here I give a short list of very interesting values, which I recommend to try yourself with pen and paper. If you want to check the optimal value, you can find this online in this link. We can get later back to this list offline after the talk. Anyways, now we have these addition-subtraction chains with free doubling defined. But now we would like to find the optimal one for given a scalar k. It seems to be a hard problem because the existence of length L addition sequence was shown to be NP complete. Sequence is slightly different from addition chain, because in sequence there are multiple values in the end, not just one, not just k, but a multitude of k's. And so this was shown to be NP complete. The NP completeness of length L addition chain with one value in the end is an open problem. The same goes for ASC star, obviously. So, but we believe that this is a hard problem to find the optimal ASC star. So what we did, we brute forced this problem for up to 12-bit scalars. As an example, this is the result for this year, 2023. And as you can see, this is a pretty subtraction chain in just 3 operations, in just 3 additions. We have the results. So there are 1, 2, 3 options. And this is no coincidence, because among all 12-bit scalars, which means from up to 4095, there's a maximum of 4 additions. Each of these numbers can be done in 4 additions, and smallest such is 683. What we do for longer scalars, we need to split k, the scalar, into shorter chunks, and that's what we describe here. For this purpose, we employ the Koyama-Tsuruoka recoding. That's an interesting recoding of integer k, which uses the signed binary representation again. And among all signed binary representation, it achieves the lowest Hamming weight, which is the same as for non-adjacent form, which also achieves the lowest Hamming weight. But compared to non-adjacent form, it has longer sequences of zeros on average, which we might see here in this example. So having this number written in binary, we can rewrite this into the signed binary in the non-adjacent representation. Non-adjacent form, it means that there are no neighboring non-zeros, so we can see that every non-zero is surrounded by zeros. Whereas in Koyama-Tsuruoka recoding, there is no such condition, but it has the same Hamming weight. So we can see 1, 2, 3, 4, 5 is the Hamming weight of this representation, and 1, 2, 3, 4, 5 is the same as for the Koyama-Tsuruoka representation, with the difference that the sequences of zeros are on average longer. So here we can see the sequences of length 2, 2, 1, 1, 2. So the average is somewhere below 2. Whereas here we have 2, 3, 1, 2. So the average is 2. So the average length of zeros is longer than in non-adjacent form. Why we need that is that we will be using the sliding window method. So we rewrite the integer k in Koyama-Tsuruoka recoding. And if there are longer sequences of zeros, there is a better chance that there would be less windows. This is a heuristic. This doesn't hold for every number. It might be improved, I admit. But as a heuristic, we believe it works quite well. So to multiply k, this crazy integer, by encrypted number c, we first we decompose this into these 3 windows, and we take each of these windows and multiply this using the optimal lower than 12-bit free doubling addition subtraction chains. We can do that. We do it here, here, and here. We can do this in parallel, and then we just apply these 3 shifts by appropriate number of bits, and then we add these intermediate values together or subtract. And that's how we implement scalar multiplication in Parmesan. Here I give some statistics. I considered 12-bit windows in this particular recoding. And so, for example, 885 is represented in the Koyama-Tsuruoka recoding. And we compare 2 methods. First, we take the standard double and add /sub, which takes the value, which reads the recoding from the left to the right, and gradually adds and shifts the number. So here we take the number, we shift, we add, we subtract, we shift, we subtract, we shift, subtract. So all we need is 1, 2, 3, 4 operations. We can see it here in this. This is also addition subtraction chain, not the optimal one, with free doubling. And we can see that this happens here: first step, second step, third, and fourth. So in 4 operations, we have the result. On the other hand, if we find the optimal ASC star for this particular number, we can do this in 3 operations only. Here's the recipe. So it looks slightly different. And that's why on average, we have 3.88 for double and add for the naive variant, and 3.1 for the optimal addition subtraction chains, which gives the 20% less operations with our optimal addition subtraction chains of length 12 bits. All right, that was for scalar multiplication. we do not have much time left, so let's go through the rest of the operations which are implemented in Parmesan. And let's start with multiplication and squaring. For multiplication, we employ the Karatuba algorithm, which uses a divide and conquer strategy and achieves O(n) to the log 3 complexity. We use this only for longer inputs, namely for 16 and longer than 18 and longer bit inputs. Otherwise, standard schoolbook multiplication is worth it better. And in Parmesan, as opposed to TFHE RS, we calculate the full result, meaning that, for example, if we input two 16-bit numbers, our result is 32-bit, whereas TFHE RS trims the result into 16 bits only. It depends what behavior you expect. This is just the way how we implement this. Then there's a dedicated function for squaring. Well, squaring is a special case of multiplication, but there might be found very interesting optimizations. And for many applications, squaring might be useful. Compared to multiplication, divide and conquer is used for fairly short inputs, actually from 4 and longer. And for 3 and shorter, we can directly calculate each bit of the result in parallel. So there are 5 parallel bootstraps, and the operation and the calculation has depth 1, so it's in single step in 5 threads. And the interesting thing is that any square modulo 4 falls into this set, either 0 or 1. So we always have 0 at 2 to the 1. So we do not need 6 bootstraps. We only take 5 bootstraps. To make a comment, there is really plenty of room for optimizations for these two algorithms regarding scheduling of the operations and so on and so forth. Then the last set of operations is our comparison-based operations. The first of them and the fundamental one is the Signum operation. And this is used for the comparison of x and y in signed binary. There is a peculiar thing in signed binary, and that's that the lexicographic comparison may fail, because in standard binary we may compare two numbers by the leading digit. We just compare the leading digit, but it doesn't work in this representation, as we can see here in this example. Here we have on the left-hand side we have a signed binary representation of 3, which has the leading bit digit of 0, and on the right-hand side we have 2 in this strange representation where the leading digit is 1. 1 is more than 0, but 3 is more than 2. So for this purpose, we cannot use lexicographic comparison in signed binary. We need to resort to a different method. And the good news is that comparison with 0 works as expected. So what we do, we subtract the two values using our favorite parallel addition-subtraction algorithm, and then we just run Signum of their difference. We implement Signum by a parallel reduction. This is a modified version of an existing algorithm. In case of Parmesan, we evaluate chunks of 4 encrypted bits as follows. And for this purpose, it's very important to use proper parameters, proper TFHE parameters, because here we take 8 times ciphertext plus 4 times ciphertext, and the noise might grow very much. And in the TFHE parameters paper, there is the value of knee squares for those who are interested. And for Parmesan, we need at least 85, and this is the highest value in Parmesan. So it's very important to choose a proper parameter set to be able to accommodate the noise from this operation. Then this value is bootstrapped. This evaluation of the 4-bit chunk is bootstrapped with the Signum lookup table, which is negacyclic. So that's a good in this point. That's a nice feature to have a negacyclic lookup table. So we can make use of the whole lookup table, including the negacyclic overlap. All in all, we reduce the n-bit number in the log4 n steps, and for this purpose we need n/4 threads. Then there's maximum, which I skip because we had lack of time. That's not much interesting. That's quite technical, and I give a small comment on rounding. There's also a peculiarity with rounding, because in signed binary, as opposed to standard binary, the value of xi-1 is not enough to round this integer at the ith position. So let's say we want to keep the values from xn to xi, and we want to get rid of the rest. We want zeros here and round this. In standard binary, it would be sufficient to take this value and add it here. If this is 0, then it adds 0 and rounds down. If this is 1, it adds 1 and it rounds up, which makes it correct rounding. But in signed binary, this doesn't work. And actually, it depends not only on the value of xi-1, but it also depends on the signum of the rest of the number from xi-2 to the end. And so based on these two values, there are 9 combinations which need to be combined together through some addition and lookup table evaluation. So it's also not straightforward in the signed binary. And here we could see that the signed binary, on the one hand, it helps find parallel addition algorithm. On the other hand, it causes certain troubles in Signum, in comparison and in rounding. So we need to find the balance, the proper balance. All right, so that was the introduction of all the operations that are implemented in Parmesan. Now we can move on to the experimental results, which we made on some powerful machines. So first, I would like to introduce the Parmesan library, which is available as a Rust crate on the standard website, crates.io. Internally, for the TFHE implementation, it employs a TFHE RS library, version 0.2, and there is a neat demo you can try and you can play with. For the setup of the experiment, it's very important to set up proper parameters. As I was talking about, we need 5 bits of plaintext space, 5 bits, actually 5 bits of the raw plaintext space. So there would be 4 bits plus 1 bit for the negacyclic overlaps, and the value of ni square greater than 85 due to the addition in Signum. So this is the technical thing. Anyway, so what inputs we tested? We tested from 4 to 32-bit input encrypted integers. For scalars, we tested these scalars because they go with some extreme properties. They are somehow interesting. So, for example, this is power of 2. This is 2 to the 12. This is 2 to the 12 minus 1. This is 2 to the 12 plus 1. So, for example, 4096 should be for free because it's multiplying by, it's actually adding 12 zeros, 12 unencrypted zeros to the end. And for these two values, there are interesting and short ASC stars. For hardware, we've chosen 2 machines, one with a 12-threaded processor. That's Euracom's internal machine, and then we chosen another machine with 2 64-threaded processors, which is a supercomputer operated by ENfra. I would like to thank to ENfra for providing the resources. And here we have a table of the results. So you might find this table in the full paper, which you can find in the description of this talk. I just give a few comments how to read the table. and maybe highlights some interesting operation. So the first line is PBS, it's bootstrapping, it's lookup table evaluation. And here so that's the baseline operation basically. And based on this, all the other timings are derived. So in the first line, we can see addition subtraction of 32-bit numbers. And this is for Parmesan on the respective machine. This is for TFHE RS. In this specific version, there's already a newer version, which is supposed to be optimized a bit better. So it might be outdated, but I wasn't able to rerun the experiments again and again because the development is very fast. Especially for scalar multiplication, I heard there are some improvements. So, for example, for this scalar, as I said, 4096, this is 2 to the 12th. So this should be trivial, which we can see in Parmesan. This is almost nothing. But in TFHE RS, it took some time. So the speed up, I just wrote something close to infinity. The speed up is just there is no lookup table no bootstrapping here, and there is some bootstrapping here. So that's why I put this infinity, but it's not really infinity. And we might also see some differences for these numbers close to 2 to the 12th, and also for the addition subtraction chains. It's also worth commenting on the multiplication and squaring. Because as I said, TFHE RS trims the output to the length of the input, whereas Parmesan outputs the full output. So if the inputs are if each input is n bit long, then the output is 2n bit for squaring and multiplication, and Parmesan doesn't trim. So basically, it outputs twice more bits, and it might be improved if the result were trimmed to n bits only. So that's why it's not directly comparable. But still, Parmesan, for example, for squaring, there is a dedicated operation as opposed to TFHE RS. In Parmesan, it's still a little bit faster. And one more short comment for maximum. It depends what's the depth of the maximums that's evaluated, especially in TFHE RS, because there is certain space that might hold some overflow for a short time, and so it might be different if this is the first level maximum or second level maximum. Meaning that what I took 4 values A, B, C, D. And I calculated maximum of A and B, then I calculated maximum of C and D, and then I calculated the maximum of maximums. So basically, I did these 3 operations, and the amortization is taken over these 3 evaluations of maximum with different levels, different depths. It shows that the TFHE RS is actually faster in the first step, but slower in the second level of maximum. Then we have a colorful figure here, and that's the second experiment where we can see the analysis of CPU load for 32-bit maximum. This is with old implementation, where bootstrapping took much more than before. So we can see that so this is, that's maximum. So first we need to start with subtraction. Here we can see the start of each operation with vertical bars, and we can see that the processor load of each of the 32-bit cores is on the maximum. Then after subtraction, there's the Signum recursion, which takes 9 bits, so we can clearly see 9 bits of the processor load. Then another step of the recursion on 3-bit, and then the final lookup table evaluation of 1 bit. So there's just 1, and in the final step there's a selector that again runs in parallel for each of the 32 bits. All right. That's it. Let me conclude my talk. This is the summary of contributions. We investigated parallel addition over TFHE encrypted integers. And on top of parallel addition, we built other arithmetic operations, namely scalar multiplication, for which we defined the specific free doubling addition subtraction chains. Then the other operations are multiplication, squaring, signum, maximum, and rounding. And all is implemented in experimental implementation, and the implementation is evaluated, and everything you can find in the PARMESAN library. And what we can conclude, for long enough inputs and enough threads, at the moment it outperforms TFHE RS in most of the operations. As a work in the progress, there are some future improvements or also alignments with TFHE RS. Regarding some future work, I suggest some directions for future improvements, which I would be happy to work on. There definitely might be more operations supported. So, for example, a fixed width operation, like in TFHE RS, so that would emulate integer XY types, or bitwise operations. There is a problem with signed binary representation, so this would require conversion to the standard binary representation. There's a bit question mark with division and modulo, because this might give not a number. This might require forks, and forks are definitely not convenient in homomorphic encryption. The other branch of future direction would be improving the efficiency. So, for example, thread scheduling for some dedicated operations and dedicated optimizations, or some batching technique. We were also thinking of scheme switching using BFB for multiplication. Another question mark goes for TFHE versus final. Which of these schemes would be more suitable for parallel arithmetics? And there's also a big theoretical question, and that's the hardness or NP completeness of addition-subtraction chains or free doubling addition-subtraction chains. So that was indeed a bit longer talk. Thank you for your attention. And now we can go for a Q&A session.